In the last video, we saw the reduced density operator, which we use to trace out a subsystem that is not of our use from a composite system. In this video, as an application of reduced density operator and quantum teleportation, which you may recall from one of our previous videos, we will rigorously see with the help of the reduced density operator concept why we cannot send any information faster than speed of light, which is obviously true from the theory of relativity. So this was the quantum circuit which we saw while understanding the quantum teleportation, where Alice wants to send the state psi to Bob through a classical channel with the help of the shared Bell state beta 00. Here M1 and M2 are the measurements made by Alice which she communicates to Bob through a classical channel. Now, to recall this state, we took the information that was to be teleported psi as a generic qubit alpha 0 plus beta 1. Also, psi 0 was the tensor product of psi and beta 00, which is equal to alpha 000 plus 011 plus beta 100 plus 111 divided by root 2. Similarly, if you recall, psi 1 was equal to this state, and the state immediately before Alice makes a measurement was psi 2, which can be given as psi 2 equal to this expression. Now, after the measurement, each term has 1/4 of probability of occurrence. The density operator corresponding to the state psi 2 can be written as rho equal to outer product of psi 2, which when calculating will get rho equal to 1 by 4 outer product of 0 into this term, where alpha star and beta star are the complex conjugate of alpha and beta. Similarly, writing for the remaining three terms, we get this expression. So, in order to find the reduced density operator of Bob's system, we'll have to trace out Alice's system from rho. Therefore, rho b, which is the reduced density operator of Bob's system, would be equal to partial trace of A into rho. So, the partial trace of Alice's system are the first two qubits of the state psi 2. Therefore, rho b equal to, now the partial trace of A would be applied to these outer product states. Therefore, if you take for example trace of 00, it would be equal to 0000 inner product, which is 1. Similarly, trace of this would be equal to 1, this would be equal to 1, and this would be equal to 1. So, by tracing out Alice's system, these all terms will vanish and we will be only left with these terms. So, rho b would be equal to this expression. Now, we can simplify this expression by multiplying the brackets, where the terms 0, 1 and 1, 0 would be equal to 0. Since we are working in our computational basis set of zeros and 1, 0, 0 will be equal to 1 and 1, 1 inner product will be equal to 1. Rest everything would be 0. So, finally, after simplifying it, we'll get rho b equal to 1 by 4 twice alpha square plus beta square, where alpha square is equal to alpha into alpha star and beta square will be equal to beta into beta star, into outer product of 0 plus twice alpha square plus beta square into outer product of 1, where the multiple of rest of the outer product except 0, 0 and 1, 1 would be 0. So, taking 2 common, and from the fact that alpha square plus beta square would be equal to 1, from the normalization condition, we'll have rho b equal to twice outer product of 0 plus outer product of 1 divided by 4. Now we know from the completeness condition that outer product of 0 and outer product of 1 would be equal to I. So this would be I by 2. Therefore, rho b will be I by 2. That is the state of Bob's system before Alice has communicated her measurement to him through classical channel is I by 2. And this state has no dependence of the information of psi that was to be teleported. Therefore, if Bob performs any measurement on his system, he will have no information of the state psi. So, we can say that until Alice communicates her measurement to Bob via a classical channel which takes a finite amount of time, Bob will have no idea about psi. And this scenario prevents Alice from using teleportation to transmit information to Bob faster than light. So I hope you understood what prevents faster than light communication.